All right, I think it's time to get started. Welcome back, folks. I hope you had a good weekend. Hope you're having a good election day so far. Um, uh, One little announcement. I got two announcements. One is I graded the test rematches. I'm catching up on all my grading. I still have two homework assignments uh, at large that I need to grade. Um, but check out your rematch. Remember, the rules for that were your final exam score that will count for you. It will be the average of your original one together with the rematch one. So look it over. If you have any questions, let me know. I'd be happy to chat about it with everybody, with anybody. Any questions about that one? All right. I had another thing. This is a strange, strange predicament that I find myself in concerning the homeworks. So as I've been looking at the homeworks, I'm going to turn off the ding dong. I notice when I'm reading the homeworks that a lot of your answers are the same as each other. It seems like you guys are working together, or perhaps either working together or sharing your answers with each other, which is fine. I wonder if you're if one of you is coming up with all the answers. Like it seems like you guys, almost all of you, are coming up with the same answers to some of the questions, which is a bit of a surprise to me. I don't know what's going on with that, and I don't especially care what's going on with that. I do feel in general like it's totally fine with me if you guys want to work together, and therefore you will come up with the same answers. I hope that you are not simply copying answers from one another. I I wouldn't exactly consider that cheating, but I would consider that an extremely bad idea in terms of your understanding the course material. To be honest, when I looked at the grades from the first test, I thought that they were kind of low compared to your understanding of the homeworks. But as I read the homeworks more, I begin to be concerned that you are giving me good answers on the homework even without actually understanding them, which is a bit of a problem in my opinion. So all of this to say, I don't know what's up with that, and I don't really care exactly what's up with that, but I consider it your responsibility to be understanding the stuff that you give me on the homework. And if you really are not understanding the homework but giving me correct answers anyway, you may get decent scores on the homework, but you will bomb the tests, and I will sleep at night like a baby. So all that to say, like, I hope that you really are doing the homeworks and understanding the homeworks, and I would be happy to discuss. You know, I think that a lot of the homework questions that I'm assigning are kind of difficult, and I'm a bit surprised that nobody comes to talk to me about them. Not that I need you to come to talk to me for like my own validation, but these are hard problems, and I hope that all of you are like wrestling with them because that's part of the learning process. I think that's all I want to say about that. Anybody have any comments? This would probably be easier to talk about if we were all in person, but anything to say about
I
that?
think I think one thing is on the homework I usually start it like on Sunday and I like go over everything for a very long time before I really understand it. So then the test, like with the time factor, kind of made it a little bit more difficult for me to like really go through it all and like look through the textbook and my notes and like make sure I understood it. So that I feel like that might have been it for me, but I don't know about everybody else.
Yeah. I mean, the test is the time pressure certainly makes it very different. It's a very different experience trying to do the test. Yeah, I get that. All right. Well, you know, if anybody has any anything to discuss with me, you know, if you want to talk about that general thing individually or whatever, please let me know. I'm into it. All right. All right. Let's get back to it then. So we're talking about continuous functions. That's what we talked about last time, and we have a few more things to say this time about continuous functions. I refresh our memory with the definition right there. This is what it means to be continuous at a point. Continuous at C, it means for all epsilon greater than 0, there's delta greater than 0 such that this business is true. X, the distance from x to c less than delta implies the distance from f of x to f of c less than epsilon. This basically means the same thing as saying lim x goes to c of f of x equals f of c. All right, which is the definition that you see in a calculus class, although I'm using the real definition of what lim means rather than just writing that thing. Okay, I thought maybe we could start with, we did a bunch of examples of this last time. I thought maybe we could start with another comprehensive exam question. This was from 2019. And in case you care, this was number 22, part A of the comprehensive exam. It says, prove from the definition of, actually I'm not sure it says of, you know what it means though. It says proof from the definition that if f and g are continuous, then f plus g. Sorry, I should say continuous at some point. So I'm going to try and squeeze that in there. Sorry about this. Continuous at a. So I'm using exactly the language that the question on the exam used. If f and g are continuous at some specific value a, then f plus g is continuous at a. All right, this is your job. Prove from the definition. That is the definition of continuity. This is part, I said part A. This is actually part B of the question. Nobody cares about that. Part A was just write down the definition of continuity. So for that, you should have just written, you know, this, what I wrote up there. And then for the part B, prove using the definition that if f and g are continuous, then f plus g is continuous. All right, this one, I'm going to give you a hint. This was not given in the test, but I'm going to say do the epsilon over 2 trick. This is something that we've seen at least once before. We haven't done a lot of examples that require this epsilon over 2 trick, but I wanted to try one like this. If f and g are continuous, then f plus g is continuous at some point a. All right. Let's start it off. I mean, we don't have to have a big idea just yet. We need to show that f plus g is continuous at a. So let's write down, using the definition, what that means. I'm going to say let epsilon greater than 0 be given. And then we'll find delta greater than 0 such that it's going to be continuous at a, right? So I'm using the definition that I wrote down before, only instead of C, the point in this example is called A. And then I have this implies. I'm looking at this part of the definition up here, f of x minus f of c less than epsilon. That's what it means for f to be continuous. I'm trying to prove, though, that f plus g is continuous. And so what I need to put in here is, instead of f's, I got to use f plus g. So it will look like f of x plus g of x. That's the f of x part. So like this part here became this. And then minus, what are we gonna say next? Oops, do this part here.
in parentheses f of c plus g of c.
Yeah, great. Our function this time, instead of f, is f plus g. And so instead of f of c, and actually it's just the point c is called a in this one. So it's going to be f of a plus g of a. I think that's what she said, right? So that's the green underlined part from before. We are using f plus g as our function instead of just f. And then less than epsilon, of course. All right. Okay, as always, we are going to try to rewrite or simplify or something using the stuff inside the absolute values on the right there. So I'm actually, the way that I wrote this little proof out, I didn't use a little sidebar, but I'm going to say we can rewrite like this. Okay, what I start with, f of x plus g of x minus, in parentheses, f of a plus g of a. All right. How can we rewrite that? Anybody have a suggestion? You want to rephrase it somehow with the goal of using the fact that f is continuous and also the fact that g is continuous. The fact that f is continuous, in order to use that, you want it to look kind of like this. And to use the fact that g is continuous, you want it to look like this, but with g's. So towards that end, anybody suggest a way to rewrite this?
Can you distribute the negatives on the right side and then put the f and g's together?
Yeah, that's what I want. Distribute the minus sign and then group, sort of put the f's together and the g's together. So I'm going to have f of x minus f of a, and then plus g of x minus g of a, right? Bad parentheses. I like that. Right, I like that because I'm going to use the fact that f is continuous, which will require something with just f's, and then I'm also going to use the fact that g is continuous, which will require something like that again, but with g's. So this, and then I can really split it into two bits like this. This is the triangle inequality. I used a less than or equal. When you split up an absolute value, a sum inside of an absolute value, you split it up into two sums of absolute values. That's the triangle inequality, which is why I use the less than or equal to sign. All right. And now, each of those two things, the idea here, so this I'll write in blue, this is sort of informal reasoning here, but this is small since f is continuous, right? And this one is small since g is continuous. That's the idea. The fact that f is continuous, the definition of what it means for f to be continuous means that we can make this f of x minus anything less than epsilon, where this epsilon can be anything we want, right? Continuous means for every epsilon you get this to be true, all right? That's sort of the key observation. Sorry, I scrolled away from what I had just written, all right? You can make those things as small as you want, and this is the epsilon over 2 trick. So I'm going to say since f is continuous, that means there's this, yeah, so I can say use epsilon over 2, and then we have, then there exists delta such that, I'm going to call this one delta, because I'm going to say this twice, once for f and once for g. I'm going to call the first one delta 1, and the one for g I'm going to call delta 2. So then there is some delta 1 such that x minus a less than delta 1 implies f of x minus f of a less than epsilon over 2. So I'm writing the definition of continuity, but since we know f is continuous, it means you can write that thing for any epsilon, and in particular I can use epsilon over 2 in this position. This is the old epsilon over 2 trick. Eventually this epsilon over 2 is going to get plugged in right here, and then another epsilon over 2 will get plugged in right here, and they will add up to epsilon, which will finish the proof. But anyway, since f is continuous, we say that. And then we're going to say the same thing for g. So similarly, there exists delta 2 such that x minus a less than delta 2 implies g of x minus g of a less than epsilon over 2, right? You can do it with f's. You can also do it with the g's, because f and g are both continuous. And the definition of continuity allows you to make these inequalities for any epsilon, so in particular I can use epsilon over 2. All right, and then how do I get, the whole goal here was to make this sum up here, come on now, my pen went out, to get this sum up here to be less than epsilon, right? That's this thing. How do we get that? Well, as long as our delta is smaller than both of these, delta 1 and delta 2, then these two things will add up to epsilon over 2 and epsilon over 2, which is epsilon. So to end the proof here, we say something like, sorry, I don't think I can fit it all on the screen at once. Let delta be whatever is the smallest between delta 1 and delta 2. And then what? Then if x minus a less than delta, we have, this is the end of the proof. I'm going to start with that same thing that you see at the top there, the absolute value, f of x plus g of x minus f of a plus g of a. This, because of what we already said, is less than or equal to f of x minus f of a plus absolute value g of x minus g of a. Oops, absolute value. All right. And then those ones, each of them is less than epsilon over 2, because the delta I'm choosing is so small that it's smaller than both of these, and so each of these things is going to be true. They're each less than epsilon over 2. So this is less than epsilon over 2 plus epsilon over 2, which is epsilon. All right, that's it. As far as individual comp questions goes, this, I would say this is kind of a hard one. I mean, it's not so hard if you remember how to do it, but this this technique here is, I think, not so simple to connect all the dots, unless you had just been reading this proof, right before the test. Are there any questions about that one? This is the old epsilon over 2 trick. We used a similar trick when we proved that the limit of two sequences adds up. If you have, the limit of an plus bn is the limit of an plus the limit of bn. It's the same proof for that. All right. Okay, great. That actually is sort of like the statement here that if f and g are continuous, then f plus g is continuous. Actually, that is much easier to prove not using the definition, but you can prove that easily using the limit rules. So remember our rules for limits. Included, there was one of them that said lim x goes to c, or I'll use a just since we're comparing with the previous stuff here. Remember this? There was a rule like this. X goes to a. I think we did this last time, right? Plus lim x goes to a of g of x. Was it last time? Remember the time before? I don't know. We had a rule for limits like that. This comes from the same rule for sequences. Our rules for limits included this. What this means is then trying to move this thing over. All right. Then if you think of continuity in terms of limits, then this actually becomes pretty easy. Then it means that if lim x goes to a of f of x equal f of a, that is to say f is continuous, and if lim x goes to a g of x equal g of a, which is to say g is continuous, then that means that you can add them up. What is lim x goes to a of f of x plus g of x? Well, you split the limit up according to our rules for limits up there. You get lim x goes to a f of x plus lim x goes to a of g of x. And this is lim, not lim, sorry. I already said lim x goes to a f of x is f of a. And then this is g of a, all right? And so down here, what this means is f plus g is continuous. So actually, you don't need to use the definition of limits. It's better to use the rules for limits, and then this thing is much easier. You get this almost for free. You just sort of factor out the limbs, and everything works out great. All right? And so there's actually, this is sort of the moral of the story here is the limit rules give us for free rules about continuity. So the limit rules give us rules about continuity, about combining functions together and getting continuous functions. So the limit rules give us rules about continuity. And I'm just going to write this as a big theorem. We're not going to do the proof. The proof is along the lines that I just said. You just rewrite continuity in terms of limits, and then you add the limits together, or you multiply the limits, or whatever. So this is very similar to the rules for limits, but it's about a phrase in terms of functions being continuous when you combine them in certain ways. So it says if f and g are continuous at, say, a point, let's say C, because our book usually uses C for the point, then, and there's 4 parts, just like the theorem about adding limits of functions or sequences. First of all, k times f is continuous for any constant k. So if you have a continuous function and you multiply by a constant, the result is also continuous. That's because the rule for limits, there is a rule for limits about multiplying by a constant. All right, so if f and g are continuous, then any constant times f is continuous. Also, this is the one that I just said, f plus g is continuous. Now we proved that one directly using the definition, although it's easier if you use the limit rules. And then we have the third one is about multiplication. F times g is continuous. And finally, the fourth one is about quotients. F divided by g is continuous. All of these, sorry, I should say continuous at C, at this one particular point. I'm not saying they're continuous overall, but for any point at which f and g are both continuous, f plus g is also continuous at that same point. At C on all of these. F divided by g is continuous. This is what reminded me that I should have said that. This is continuous at C unless g of C is 0. All right, that because then you're not allowed to do the division. All right. Any thoughts about those? These are things that probably you talked about this in calculus class. I don't know. If you have continuous functions and you add them together or multiply them by each other or multiply them by a constant or divide them, the result is still continuous apart from this business about when you divide. Sometimes you got to make sure the denominator is not 0. All right. Once you know this, actually you get sort of automatically, this means you can immediately say many functions are continuous. For example, this means any polynomial is continuous. Why is that? It's because any polynomial can be written as just adding constants together and multiplying by x, right? If you want to get, say, x squared, you go multiply x times x. But each of those x's is continuous. So this means any polynomial is continuous, just as a little justification. And I should say, sorry, continuous, not only at a particular point, but continuous on all of R. That is, it's continuous at every point, at every real number. Any polynomial is continuous all of R. Why is that? It's because it comes from a sum and product of constants and x, like f of x equals x, and that is continuous. And then if you add constants to it, multiply by other x's, multiply by other constants, you can get any polynomial by combining those things. And because of this theorem there, such a thing will still be continuous. If all you're doing is adding and multiplying by constants and multiplying by each other, it's still going to be continuous. All right? Any polynomial is continuous on all of R. And you can even divide. If you divide, you don't get polynomials anymore. You get other things. So those other things are called rational functions. Let me just say also any rational function. That means a ratio of polynomials. A fraction with a polynomial on the top and a polynomial on the bottom. Any rational function, by exactly the same way, is continuous, not necessarily on all of R, but on as long as the denominator is not 0. I'm going to say it this way: any rational function is continuous on all of its domain. Right? There may be certain points for which it's not continuous, but those points are just because the function isn't even defined at those points because of the 0 in the denominator. So any rational function is continuous on all of its domain. I'll just say parenthetically, whenever the denominator is not 0, right? A rational function is always continuous on all the other points. It has certain points where it's not defined, but otherwise it's continuous everywhere. All right? These are things, I think we all know this, right? Polynomials are continuous and rational functions are continuous apart from their individual values. Any questions about those? All right, I wanted to, just before we move on to something a little different, I would like to revisit one of my favorite functions. Remember this one? Thomae's function. This is that weird one. A couple weeks ago I described two weird functions. This was the weirder of the two, and it's hard to draw the graph of, but I put it up here. This one, remember that one? This is the one where you look at f of x is, you get 1 over n if x is a fraction, m over n, when written in a lowest form, like a reduced form, the fraction, and then you get 0 if x is not rational. All right, and the graph looks something like this. This is actually, what you see there is just a piece of the graph between the interval from 0 to 1 here. Oops, I need to write that. And what I said on that day when I first showed this to us, but we didn't try to justify this at all because we had only started talking about it. I was just giving this as an example to blow your minds. I don't know if your minds were blown, but here what I said at that point was f is not continuous at any rational point, and that f is continuous at every irrational. So I would like to try to actually demonstrate that now that we have some real definitions for everything. Can we actually demonstrate that f is not continuous at every rational and it is continuous at every irrational? So I'm going to slide back down to the bottom here. You don't really need to remember the picture. I was just trying to refresh your memory about this weird function. All right, I will write the definition again. F of x is, if x is a rational, you get 1 over n, where x is the fraction m over n, and you get 0 otherwise. if x is not rational. All right. And maybe I'll write this as a theorem. F of x is continuous for, I will say, at every c not in Q, and f of x is not continuous at every c in Q. All right. So there are two separate things that we need to try and convince ourselves of. One is for the rational points, it is not continuous, and for the irrational points, it is continuous. So maybe we'll start with the rational points. So this whole proof is just like in two big separate sections. There are two statements to prove here. Let's do the second one first. So first of all, let's consider C in Q, and I want to show that F is not continuous. Am I doing all right so far? Everybody still here? Sorry I haven't asked any questions lately. I'm feeling great. It's keeping my mind off the election. It's good for me. So what about when C is rational? All right, in this case, the idea is, remember this function, at every rational value, it has these like individual points to it, which have to do with what the denominator is, all right? But you can tell, I think this fact is kind of intuitively obvious when you look at the graph. The rationals are all like individual isolated points on the graph, and they are definitely not continuous for that reason. It's because, if you asked me from a more technical point of view, near this point along the x values, if I look at like a little neighborhood of x values around that point, many of those values in that neighborhood are nowhere near this point up there, right? They are much further down. Maybe even all of the values in that neighborhood, but certainly many of them are way down. So this is the idea that I'm going to try and write in detail. So if we assume C is in Q, just so that we can talk about the definition, right, I'm going to write C as a fraction, m over n, and then f of C will equal 1 over n, right? That's the definition of Thomae's function. You write the fraction in reduced form, and then the value of the function is 1 over n. And I will just point out for emphasis, this is not 0, right? 1 over n, whatever it is not, it can't be 0. Okay? Now, to show f is not continuous, we'll show f is not continuous using sequences. This is how you should always show something is not continuous. Showing something is continuous, usually sequences is not helpful, but showing something is not continuous, you almost always want to use sequences. And the way to do this is you choose a sequence which converges to C, but then you demonstrate that f of the sequence does not converge to f of C. So I'm going to say we want a sequence xn converging to C, but f of xn does not converge to C. All right, that's the idea. Sorry, not C there. Does not converge to f of C, right? And of course, C is m over n. F of C is 1 over n, which is what I just said before. All right. You need a sequence of points which converges to C. So on the picture here, if I could zoom in on the picture, like this point right there is C. And this point up here, the y value is, well, this is C comma f of C. The y value is this, f of C. All right. Which is 1 over n, which is, like I said, not 0. Can anyone perhaps think of a sequence of points which approach C, where when you plug them into the function you don't get f of C, that is 1 over n? It's not quite obvious. Any thoughts? How about this? Would you say I think inside this little interval down here, there is in fact many points where their y values are 0, isn't it? Anybody agree with that? Are there points around here in this little neighborhood? Are there points in there where the y values are actually 0? What would you say? Yeah, any irrationals have y value equal to 0, right? And are there any irrationals in here near this point? Yeah, there are irrationals everywhere. Okay, so we want to find a sequence converging to C where the y values are not going to 1 over n. If we choose irrationals, then their y values will always be 0. So they will not approach 1 over n, right? Which is what we wanted over there. So the idea is I'm going to choose a sequence of irrationals xn which converge to C. Is that possible? Yes, it is. Any rational number can be approached by irrationals because because of like the density property, there are irrationals everywhere. But actually, we can say pretty specifically, what's my favorite like sequence which converges to C? Usually I would use something like C plus 1 over n. But if I want to make them all irrational, I can use xn equals something like C plus pi over n. Or you could use root 2 over n or something. This is a sequence. I hope you will agree with me. All of these are irrational because C is rational, and then I add to it pi over n. It's going to be irrational. But the limit of this sequence is C, right? Then xn are all irrational with xn approaches C. So this is like, most of my sequences that I create involve things with 1 over n in them. But if you want to force it to be irrational, you can use something like pi over n or whatever, square root of 2 over n, whatever you want. Some irrational number there. All right, anyway, then x is irrational with xn goes to C, but f of xn, what is that? Well, these are all 0 because they're all irrational. All right, and so that means that f of xn does converge to 0, not 1 over n, right? We had to demonstrate that f of xn does not converge to 1 over n. Sorry, it's under my head, right? We had to demonstrate f of xn does not converge to 1 over n. Well, here it is. F of xn does converge to 0, which is not 1 over n because 1 over n is not 0. All right, so this is the end of that little proof. You choose a sequence of irrationals, and you get 0. Any thoughts about that? Any questions about that? We got 10 minutes left. Let's do the other half. This was the irrational, so we just showed that f is not continuous at some rational. Did I say it backwards before? F is not continuous at any rational point. That's what we just demonstrated. How about the irrationals? Let's talk about the irrationals. So this is sort of second half of the proof. What about C being an irrational? All right. And for this one, we're going to just use the epsilons and deltas. So we're trying to show in this step that F is continuous. So we're trying to show F is continuous, then I'm going to do the usual, let epsilon greater than 0 be given. We'll find delta such that I go x minus c less than delta implies f of x minus f of c, right? What can I say? What is f of c here? I'm about to write f of c, but actually you can say what f of c is.
0.
It is 0. Yeah, this is the case when c is irrational. And so the definition of the function I'm talking about is f of c is 0. So actually, can I just say like that, right? Right here, usually you would see f of c, but in this example, f of c is 0. And so we don't need to include that. All right. So to show f is continuous, you let epsilon greater than 0 be given, and we have to find some delta, which makes f of x less than epsilon whenever x minus c is less than delta. All right. And the idea here actually is the same idea that I tried to get across the first time that we talked about this. And so I'm just going to say, remember, if c is irrational, then what are the denominators of rational numbers very close to c? I'm going to say rationals very near c have very large denominators. All right, this is something that I did. I actually sort of got my calculator out to do specifically an example of this when we talked about this earlier. But if you think about, like, for instance, pi, the number pi, rational, what are some rationals that are very close to pi? Well, you got 3, you got 3.1, you got 3.14, you got 3.141, you got 3.1415, etc. What are the denominators of those? Well, this is just 3 over 1, which has a fairly small denominator. This is 31 over 10, which is a bigger denominator. This is 314 over 100. Now that one you can reduce the fraction, but I think you can only take out a 2, or maybe a little more. But anyway, the denominator here, it can be a little smaller than 100, but not a lot smaller. This is 3141 over 1,000. Here the denominator is 1,000. I don't know if you can reduce that, but I hope you agree with what I said. Rationals that are very close to an irrational, they must have very large denominators, and as they get closer, the denominators get even larger, right? That's the idea. I hope that you agree with that. This I'm saying, this is a little informal. This could do with more justification if I was trying to be extremely detailed about everything, but rationals very near C have very large denominators. What that means is we can choose, come on now, we can choose delta so small that any rational, I'll say any rational number x with x minus c less than delta will have denominator greater than 1 over epsilon. Here's the trick. You imagine epsilon is very small, then 1 over epsilon will be a very big number, and you want to choose the delta that's so small so that any rational that's that close to c will have this kind of huge denominator greater than 1 over epsilon. How do you know that's possible? It's because we know as you approach an irrational, the rational numbers that approach an irrational must have very, very big denominators. And so we can make the denominator super big to the tune of 1 over epsilon, all right? So we choose the delta to be that small. Okay, and then the rest of the proof sort of works out nicely. So we have to demonstrate this, right? But I've already told you what the delta is, and so now I'm just going to try to finish the proof. Now, choose that delta. There's actually 2 cases. I want to show that f of x is less than epsilon. well, can I, let me say it this way. Now to show, to show x minus c less than delta implies f of x less than epsilon. There's actually two cases. One is very simple. If x happens to be irrational, then f of x is 0, because that's the definition of f. When it's irrational, you get 0. And so f of x less than epsilon automatically, because epsilon is greater than 0. What about if x is irrational, or if x is rational, if x in Q, then I chose the delta so that the denominator will be more than 1 over epsilon. That means absolute value f of x. The definition, of course, is 1 over n, right? Where n is the denominator of x. But I made the choice of delta so that that denominator will be more than 1 over epsilon, which means this will be less than 1 over epsilon. I replaced the n by 1 over epsilon. And this, of course, is epsilon, as desired. So if x is irrational, then you get it automatically. If x is rational, not automatic, but you still get absolute value f of x less than epsilon, which is what we wanted. All right. Thus concludes the proof that the Thome function has this weird property, that it is continuous on all irrationals, discontinuous on the rationals. I think it's a cute little example. Tell your little brothers and sisters, blow their minds. They probably will not know what you're talking about. All right. We got 2 minutes left, but I think maybe this is a good place to stop, because I was about to start talking about something a little bit different for next time. So I think I will leave it at that. All right. Please let me know if you have questions about the homework. I would love to discuss the homework and help you to wrestle through the problems on the homework. Of course, I hope that you will talk to each other about it if you want to. Just be responsible. All right.
Thank you.
All right. See you all tomorrow.